Okay guys, let's continue with the introduction lecture of this week. After playing the buzzword bingo, we will have a recap of KDD1. And first of all, we will begin with an overview. So this is section 2.1. Yeah, so recall that we are usually concerned with inductive learning, so machine learning, the inductive way of deriving patterns from observations, and there are basically two general ways to do that, general classes of patterns we can search for. And the first one is unsupervised patterns or unsupervised methods, where we typically don't know anything about the data. We just have the data, and we want to try to come up with some patterns that have not been found so far. And the three typical sub-methods of unsupervised learning is clustering, outlier detection is the second one, and association rule mining, or more general frequent pattern mining. We will have a closer look on all those three later on. And then very, very often you already have some knowledge on your data in terms of, for example, some example data for some classes, so-called training data with class labels, and you want to find rules how to classify not so far labeled data according to these class labels. And in that case, you are in a supervised setting. Meaning that you typically do classification or regression, and again, we also will come to the to this class of methods in the next podcast, or one of the next podcasts. Have a close look there. Okay, so those methods we get to know in KDD1 are basically from these two major classes of methods. And this is an observation. You just have to trust me if you didn't attend KDD1, but if you attended KDD1 before, then you probably observed that most of the methods we covered there assume the data to be in a very special format and a very special structure, which is so-called feature vectors, which is more or less the same like relational tables. Yeah? And this has a very big advantage because we don't have to care too much about the representation, but we can just concentrate on finding patterns. But of course, the question is, what if we don't have those feature vectors? But before we take care about that, we asked or we try to figure out what are feature vectors actually. So feature vectors, usually you have a set of a domain, a set of objects, and a similarity measure on these objects. And that's actually a feature space. Yeah. So the domain can be anything. And the similarity measure, or more often you work with distance measure, can be virtually anything, but very often you try to be in a so-called metric space. That means that the distance measure has specific properties. In this case, it is reflexive, positive, definite, symmetric, and meets the triangle inequality. The reason why you want to have metric space is mostly because it's mathematically easy and handy, but you very often, especially the triangle inequality, is somehow counterintuitive in many applications that this really holds. So very often you have feature vectors, feature spaces, object representations that are not, and a distance function that is not a metric, and still you are happy if it behaves, the distance behaves like a metric. It's then called a so-called pseudometric, for example, and still your methods usually work with those kind of distance measures. Yeah. So metrics or the metric property or properties are not so important in practice. So even though people, especially in the research community, make a lot of ado about it, in practice it doesn't make so much, or it doesn't play such a important role. So the canonical metric feature space we usually also used in KDE1 was the following one. So here you have the domain is just r to the power of d. That means the objects have d attributes. You can consider this as a table in a relational database management system, or just an Excel table, an Excel file, where you have d columns, d attributes, and each of those attributes are real values. So you basically end up being the objects being points in a d-dimensional space. And to compute distance, similarity or distance between those objects, those points in a d-dimensional space, you can just use the so-called direct distance, airline distance, or in mathematical words, the Euclidean distance, which is just shown here. And you just take the distance between the individual attributes to the power of 2, so squared, sum that up and take the square root, which is just the direct distance between 2 points in a given d-dimensional space. So as I told you before, it's very handy to have a fixed representation, a standard representation for all your methods, because you don't have to take care about the representation of the objects. You just take care about the patterns, the methods you use. But the question, of course, is can you just fit any data onto a feature space, or in other words, can you derive feature vectors for any kind of object representation? And well, the question is, in general, yes, but of course it requires a lot of effort. And in especially the first, I would say, 50, 60, 70 years, even nowadays, still what you do is you explicitly model the features in terms of you just define features which are important for your application manually. And we will have an example on the next slide. The problem is that it requires a lot of engineering. It requires a lot of domain knowledge, because only if those features that you define and derive are really, really good and really, really suitable for your application, you will have a chance to find patterns. This is actually, again, this shit in, shit out problem. If you have shitty features, you will probably get shitty patterns. But yeah, I think you can imagine that. So anyway, it requires a lot of engineering, a lot of manual doing, a lot of expertise, domain knowledge, domain expertise. But in principle, it always works. As long as you come up or find suitable features, you are fine. And this is, so explicit modeling of features is something, so feature transformation is something you typically do in the pre-processing steps. And now you see again why those pre-processing steps, in this case the feature transformation, is extremely important, because if the features are bad, your patterns are probably for the trash bin. Then there is some kind of orthogonal way, which is called implicit modeling. Here you use kind of implicit transformations. For example, a kernel is something like which we got to know in KDE1 kernel methods. A kernel is a kind of implicit feature transformation, because here you take in the end any kind of representation, define a kernel function on it, and use the kernel function as similarity metrics. So for example, you can come up with a so-called shortest path kernel for graphs, which is a similarity model for graphs. And then you can plug in the kernel if your method allows the kernel trick. For example, support vector machines, as you probably recall from KDE1, allow the kernel trick. So you can classify graphs if you use a shortest path kernel. But again, you have to be clear that the design of the kernel is something like a manual feature transformation in some sense. So if you use a different kernel for graphs, you will get different patterns, of course. And then nowadays, of course, there's the big ado about deep learning algorithms, and one of the big advantages of the deep methods are that they implicitly learn representations. Yeah, so you can learn representations not only through deep learning, but especially deep learning approaches. Think about all these image classification stuff. What these hidden layers in neural networks do is they learn specific representations, and of course you can use these representations to do other things like neural networks do. Yeah, typically those feature learning approaches work better for supervised settings and unstructured data, and usually they need a lot of training data. So even though this seems to be very appealing on this slide here, maybe that with deep learning, you can even learn representations. This traditional way of modeling things explicitly is very often still the way you have to do it, because these deep learning approaches, they don't work too good with structured data. So usually you need some unstructured data, and you need a lot of training data. Of course, nowadays also these transfer learning stuff works with less training data, but still usually you need a lot of training data. So don't get this slide wrong, that feature learning, representation learning is best always. Very often it is very good still to do the explicit modeling, the explicit feature transformation. And this is how it has been done from day one in machine learning, so to say, and it's still very often been done today, even though we have these deep learning things. So that's why we have a closer look on these feature transformations. So this explicit modeling, once again, you try to extract features, characteristic features. Usually you try to that the features are numeric for each object, and then each object is represented as a high-dimensional feature vector, as we have said before already. And the characteristics, the characteristic features means that the vectors, the resulting vectors of the feature transformation, if they are similar, they indicate that the objects behind those representations are also similar. And that is obviously only the case if you really grab characteristic features and not some arbitrary features. So here are some examples that may work or may not work for feature transformations for different complex objects like images, CT images, time series, 3D objects, maybe some construction paintings and stuff like that. So you can, for example, use histograms, color histograms for images. Yeah, so color histograms for images. What is that? Well, you just say, okay, let's take say 64 colors, and then we just count for each image how many pixels of one of these particular colors are in this object, in this image. So each image will be transformed in a 64-dimensional feature vector, yeah? And each of the individual features tells us about how many pixels of this particular color is in the image. And if these two images here have very similar color gradients, a lot of green stuff and a little bit of orange or red, so they may have a lot of so they may have very similar color histograms. So if you want to compare images according to the color, it may be a good idea to use color histograms. If you are more interested on the objects in the images, color histograms are probably not the right thing. So that's what you have to consider if you think about characteristic features, characteristic for your application. That's very important. Yeah, that's it for the introduction, for the overview. And in the next podcast, I will tell you a little bit about clustering methods. So a recap of the clustering methods from KDD1. Stay tuned.